So, and I'm going to temporarily, just be real quick, bring up the slide. So you should all see my PowerPoint slides. Is that correct? Anyone not seeing it? Oh, and by this way, the lecture is being recorded, just so you know. So do a quick chat type if you do see the presentation online, the PowerPoint presentation. Can everyone hear me still? Oh, yes. Okay, great. Yeah, I see all the yeses now. A little bit of delay sometimes. So, time for Michael. You ready to jump in and share your screens, Michael?
Yeah, I can do that.
Okay, so we're handing it over to Michael now. I will stop my sharing too, just to make sure that there's no conflict.
So it's opening. I'm also using my phone's hotspot because my internet is down for some reason. I have no idea why.
Yeah.
So I don't know how well the connection
So I
is
see your
going to
slide.
be.
I see your slide now.
Cool.
So I'm going to mute myself so to keep the background noise in. Again, reminding people when you're not speaking, mute so that we don't get a bunch of extra background noise and makes the sound a little cleaner.
Okay. So can everybody hear me? All right. Then I will begin. So we're talking about Red Star OS, and we left off before where Nathan was talking about how Red Star was very similar to Fedora and based on Fedora, and it started out with a Windows-esque type of format, and then from that picture that we saw with Kim Jong-un on with the Mac turned into what we see here as the OS X style. And so we still don't know much about it, even though we have pictures and we've been able to download it and use it. I personally have not used it though, or downloaded it, or wanted to download it. So we're going to talk about the security now and how that is with the Red Star OS. So first, I kind of want to ask everybody, like, do you guys think that North Korea uses internet, or like, how do you guys want to, or like, how do you think that the internet is over in North Korea? What about smartphones? Like, just presenting it to you guys. You can either type it in or. So yeah, full of propaganda. Yeah, that's pretty good. Worse than China. Ah, yes, pigeons with USBs. I'm pretty sure that's exactly what it is. Yeah, so they do have internet, but it is very, very limited. And what they're trying to do, it's limited to just a handful of websites, and most of those websites are going to be full of propaganda, if not all of them. And then they do have smartphones, but that again, they're on only the limited cell services that, or the one cell service that they have there, I guess. And then so it's really hard for them to access other technologies as well. So doing a closer look into the operating system. So the operating system actually has like whenever they're taking a look into the operating system itself, they found a binary and took. So this was the down here, the insinuator.net. This is where I got this information. They looked into the binary and found this GPS watermarking information binary. Whenever you would plug in a USB, it would actually go and watermark the like if it was a picture, sure, I might watermark it, but that's not necessarily what we're talking about. It would watermark every file inside that USB. Like you didn't even have to open the file. It would just go through and just put some extra little bit of code that would start, I guess, GPS track it, as it says right here. And so over here, you can see the other interesting names that you found in the binaries of the OS. We also had the installed firewall, extra protection for the stir files, and then a crawling program. And this crawling program was pretty cool because it would go through the core system files, and it would just be monitoring all those. And if anything, then it would just fix it. It would be like, okay, I see that somebody messed around with this file, so let me just fix it real quick. And so, yeah. So is it secure? From Vice.com, I found that they were talking about it, and it said all of these changes aren't likely designed to protect the system from outside hackers, say a foreign nation attempting to remotely hack into North Korea's computer system, but all these changes for the Red's own users. So they're not it's not meant for the like outside hackers necessarily. And so I actually found another article from the hackernews.com that talked about this and how this one group called I think it's called like Hack House or something. They use this mail to our URI request to run commands on the operating system itself. And so, in short, the security fault can be used to easily install the malware or exploit PC runnings on the Red Star operating system. So that also like talks about or like we could see that that it's secure, but it's only secure because it's trying to keep people from changing the operating system or being able to get outside the internet that it's currently on. But it's not secure whenever it's going into these people are trying to hack into the system. So in short, what is Red Star OS? It's the most secure in a totalitarian society trying to keep tabs on each of your systems, but kind of, not fully, but yeah. So are there any questions? I don't know if they can use other operating systems. I know there's like 4 different versions that we know of Red Star OS. And the 4th one we haven't got a hold of. But yeah, I'm guessing no as well. I mean, yeah, I'm sure that this is definitely holding back the technology in North Korea. North Korea itself is not the most technologically advanced nation, but yeah, I don't think this helps. I mean, it's definitely a push towards going into the more technology. I don't know. I feel like I would be scared if like North Korea was more technologically advanced. Any more questions? All right. Then I will mute myself and hand it off to Professor Lim.
Okay, great. So Michael, I hope you're seeing all the clapping emojis, and now we have clapping dogs from Daniel. So
yep, I see that.
So let's see. Let's share my PowerPoint slides again. So hopefully you can all see that. If not, let me know. Gotta get focus there. All right. So next up is the Kali Linux team. I'm not sure whether it's Josh, Jacob, or Ochir that's going first. Can one of you chime in or chat which of you will be up next? So not only do we know, but don't only do I know, but the rest of your teammates know who's going to be firing up next. And then also, if you are next, if there's going to be issues with not having a microphone.
Hello, can anyone hear me?
Yes, I can hear you.
Yeah. Next, I will be first, then
Okay.
Jacob, then Joshua.
Okay. And I know that Ochira, you have a speaker, and I noticed, I believe that Jacob did too, because I saw a webcam. So I'm guessing Jacob also has microphone. And I guess we can figure out if Josh can chime in, or we will figure it out as when we get there. That's
yeah,
a couple.
Like I was talking on Monday.
Okay. Yes, that's right. I remember that now. All right. So I think we're good to go for the next one. And then Jessica, who is also set up, will be doing haiku after that. So we do have the Chapter 4 programming assignment due Friday, March 27th, which is pick any of the programming assignments on threads that you like. I have some submissions already. It should be pretty easy. One thing I would ask you to do is to submit both your executable and your source code if you could, and that would be great. So moving on, we are on slide 51 of process synchronization. Okay. And I am going to share that one. Okay, so we're almost done with synchronization. Just going back a little bit here. We were discussing monitors and how they're a very nice mechanism to make doing synchronized methods or synchronization of threads and processes easier. That it's built into languages, and in fact, there's even an operating system that has it as a key component of it. And anyway, we are now going to look at, briefly at some alternative approaches. One is transactional memory. So this is a state where the memory is set up to have a transactional nature, where a process can designate that they're going to access the memory and lock other people out from using it, and it's actually access to that memory is not allowed until the transaction can be completed. This is very analogous to a database with transactional processing with a database. Another approach is OpenMP, which is multi-threaded processing. This is heavily used by the supercomputer community, but also other people are starting to use that as a way to avoid having to control the synchronization explicitly. These approaches are less explicit, although there is directives in OpenMP that tell you which sections of code are critical sections and which are not. But you don't have to worry too much. You don't have to handle the details. The compiler takes care of that. And then we have completely different approach, which is functional programming languages, which doesn't have to deal with this, that they're written in a functional way, but it's a completely different paradigm for writing programs. One example of this that I'm aware of is Haskell, is one of the functional programming languages, but we'll go into this in a little bit more detail, not too much detail. So here again, we have transactional memory. A memory transaction is a sequence of read-write operations to memory that are performed atomically. So basically, it's like a database, and it's until you do a commit, no one else can access that particular data area. OpenMP, here we have the Pragma OMP critical, which says this is a critical section, and it's count plus equals value, which means that the compiler will take care of the handling that no one else can access this particular section of code at the same time as another process or thread. So again, it's compiler directives that are built in, and the compiler takes care of that with the parallel programming. Again, heavily used by supercomputing usage. And so here we have functional programming language, which is a completely different paradigm, as I said. Variables are treated as immutable, like strings in Java, and cannot change state once they have been assigned a value. There's increasing interest in functional programming languages as Erlang and Scala, and then Haskell was another one that I mentioned. So this is, again, a different paradigm where you don't have to worry about data race conditions. And that is it. I went through that pretty quickly, but does anyone have any questions regarding those? Okay, so I would like to go ahead and go through those slides again for process synchronization, because it was a large chapter, and again, like I said at the beginning, I think it's a area that I definitely want you to be familiar with. So. Okay. Let's share. Okay. So chime in if you don't see the PowerPoint slide. I think I have that up and available. All right, so I'm going to head on down and try to pull out some key things. So we have a common situation where synchronization is involved is the producer-consumer problem, which is someone writing into a buffer and someone reading out of the buffer, producer waiting for a buffer to be available to write to, and the reader, the consumer, waiting for information to be available to take it out of. A race condition. Key thing to remember here, please keep this in mind, is a race condition results when several threads are trying to access and modify the same data concurrently. If they're trying to access it for read, it's not a problem. But when it becomes a problem is when they're trying to access and modify the same data concurrently. That is when we get a race condition. So those two conditions need to be present in order for it to be a problem. So one thing here, we have the preemptive and non-preemptive cases. A non-preemptive kernel is safe from race conditions on kernel data structures because basically a process or thread cannot be interrupted. And so it can actually rely on having exclusive access to the data because it knows it won't be interrupted. So non-preemptive kernel is safe from race conditions. Preemptive, then you have to handle race conditions and critical section handling. So here we have synchronization hardware and the atomic instruction. Key thing here is an atomic instruction executes as a single uninterruptible unit. That is the definition. It could be multiple things going on, multiple different instructions that are built upon, but an atomic instruction executes as a single uninterruptible unit. It cannot be interrupted, is the key thing for the atomic instruction, hardware instruction for supporting synchronization. Race conditions are prevented by requiring that critical regions be protected by locks. And we see that locks can be created by semaphores or it can be part of monitors. But again, race conditions are prevented by protecting critical regions with locks. Okay, here we have semaphore usage, and please keep in mind there are two categories of semaphores. We have the counting semaphores, which has an integer value that basically ranges over unrestricted domain, which means they can go negative. They could be 0 or positive numbers. A binary semaphore is only 0 and 1. So a binary semaphore essentially behaves as a mutex lock because it only has values of 0 and 1. So again, these are the two different categories or two different types of semaphores. So semaphores are a valuable mechanism but the method for making semaphores more efficient in terms of not having any busy waiting is having a waiting queue, enlisting a waiting queue in which waiting processes can be queued up. They're blocked and then wake up, and when they're woken up, they are removed from the process queue. So again, this is a key part of semaphores. It is the waiting queue that makes them efficient. Okay, deadlock is sometimes referred to as a deadly embrace. A deadlock-free solution can still result in starvation. So you can still have a situation where you've solved the deadlock problem, but starvation, or basically a process may indefinitely wait, is still a possibility. One example of this is priority inversion, in which a process with a lower priority than a higher priority has a resource that the higher priority process needs. The solution for solving that is that when the lower priority process is using the resource that is required by the higher priority process, its priority is escalated to that of the higher priority process that needs the resource that it's using. So that is priority inversion. So one thing that keep in mind here, this is Dynamics philosopher's problem, and this is a solution using semaphores. Here we can see that mutual exclusion is ensured, but deadlock prevention is not in place. But as we go down to the monitor solution that we discussed, we're going through, let's see, kind of skipping here. Okay, one thing is, so monitors are generally part of most modern programming languages, and basically there's an entry queue and a queue associated with each event. And so those are the condition variables. And so we came up with a solution to the dining philosopher's problem. And here we have mutual exclusion, no deadlock, but it still has the possibility of starvation. But we have solved the deadlock problem in the monitor solution for the dining philosophers that we have here. Okay. All right, so that concludes our discussion of process synchronization. Does anybody have any questions regarding process synchronization now that we've finished up with it? And I shouldn't probably have closed the PowerPoint presentation unless you wanted me to, in case you wanted me to go back, but let me know. And certainly feel free to email me a question if you go through the material and you see that there's something that you don't quite understand as well as you thought. So just sort of a heads up about where we're going in this class. One thing is that there is a chapter on starvation and deadlock, and in particular focusing on deadlock. It is a very difficult problem to solve, and is an area that you probably won't have too much direct exposure with. So it's more of an academic exercise. So I will go briefly over some of the slides for deadlock and starvation, but I plan not to cover it in great detail unless we have time at the end of the semester that I need to fill. But in the past we have covered it, but since we're online and it's completely new to us, we've been asked to cut material from our classes, and that is certainly an area that is a very low priority. So we'll go over it briefly, so there will be some coverage of it, but it would be very, very short. So anyway, let's go on to CPU scheduling.
Mr. Lim, Jason has a question in the chat.
Okay, thank you. Let me scroll down and see if I can scroll down without muting my mic. Okay. Oh, Jason, okay. Is there any kind of downside to non-preemptive kernels, by which I mean, why do we futz with race conditions at all if there's a... So one of the things is that it's a performance issue, Jason. If we have a kernel that is not, or that is non-preemptive, or we have code that is non-preemptive, then you lack the ability to have progress happen in multiple areas. So if you actually did that, in particular, as we go into CPU scheduling here, so this is a great lead in to the next chapter. If you had I/O operations and you had everyone non-preemptive and they're not allowed to get in there, we would have a great performance issue. Now, you could certainly self-preempt yourself when you do an I/O operation, and that would be fine. But it's basically a huge performance hit to have it such that it's non-preemptive. Again, if your kernel is small enough and operations are quick enough, you can get away with it. But in terms at the level of the layers above the kernel, you would definitely have a problem. The performance would be severely degraded to the point where it would be a great problem. Now, one of the areas where you do see non-preemption used is real-time operating systems, because in particular with real-time, oftentimes you have control over exactly what's happening. There aren't multiple applications that you're competing with. There's known processes that are happening in the real-time realm. So you can possibly get away with that because you will have direct control, or you can have direct control over what processes are doing what when. So a non-preemptive solution could be used for a real-time operating system, but again, it's not the norm. It's more of an outside situation. So anyway, thank you for letting me know that I had missed the chat message, because I generally don't go over to the chat one and scroll, because I learned in my last lecture, for those of you in my software engineering 1 class, when I use my scroll wheel, which is my instinct to use my scroll wheel rather than to drag and drop, but use my scroll wheel. When I use my scroll wheel, it mutes my mic. And so then I get a bunch of messages saying, you muted your mic again. So anyway, sort of the adventures of going online. We found a defect in their system or my driver, where when I use my scroll wheel, it causes my mic to mute. So, okay, so chapter 6, CPU scheduling. Chime in either with your microphone or chat if you can't see them, but I am assuming it's highlighted in red, so I assume I'm sharing it. So chapter 6 is on CPU scheduling, and so the basic goals is to introduce CPU scheduling, what types of algorithms are used for determining which CPU processes are running for a multi-programming operating system. And we describe various CPU scheduling algorithms, like I said in the previous bullet point, and we discuss and evaluate the criteria for selecting the particular algorithms and when they're most efficient and when they're not such a good idea. And then to examine some scheduling algorithms of several operating systems. I don't know if I will go into that one. We probably will not cover that, but we'll see. see how it goes. So in answer to Jason's question, I came up with the CPU versus IO. And so this actually tends to be the most dominant case for switching out and in and out of the process, basically causing a context switch. And so a lot of the analysis for this, for algorithms for swapping in and out and scheduling processes into the CPU revolve around this, that you tend to have a big burst of CPU usage by a process, and then it has to do some type of I/O, either accessing a file on a disk, going out over the network, whatever the case may be, and this happens at a slower speed than the CPU. So we actually do have CPU cycles that are available, and that's the I/O burst, and that's where you're actually waiting on some external device. So you basically have these periods of CPU and I/O usage, and the plan is to try to do a constant switch out of the CPU and allow someone else to work when I'm in the middle of an I/O burst and waiting for I/O. So that's the main gist of it. So basically, those are the bullet points. If you have any questions, chime in. Otherwise, I'm going to keep moving forward because I think I covered everything in those bullet points. So CPU scheduler. So we have a short-term scheduler which selects from among the processes in the ready queue and allocates the CPU to one of them. The queue can be ordered in many different ways, and the decision on which process gets switched in from either from the ready to the running state or the running to the wait state are all critical. So the decisions are switches from running to waiting, and I said that one example is I have an I/O operation I'm waiting on that would put me into the waiting state. When you're switching from the running to ready state, which is you're basically saying I'm not ready to run. I'm ready to run, but I'm going to actually it's the scheduler that decides let's let someone else work. And so that will be another context switch case. And then we have switching from waiting to ready, and that happens when an interrupt occurs that says my I/O operation is complete, and then we are switched back into the CPU to presumably handle the data that I got from the I/O operations. And then the last one is the task of the process has completely finished and it terminates. That would switch us to the terminated state. So scheduling under 1 and 4 above, so it switches from running to waiting state and terminates, is non-preemptive because we have voluntarily removed ourselves from the running state for the CPU. But the other two are preemptive, and that's when you're involuntarily switched from the running to ready state. And when we're in the waiting to ready, that happens from an interrupt from the I/O. So again, that is preemptive. The process that was in there gets preempted by the fact that the I/O operation has been completed. So that is an area where non-preemptive would not work too well because of I/O. It would be because of I/O operations. Sorry. So all of the scheduling is preemptive. Consider access to shared data. Okay, so that's our synchronization mechanisms that we talked about in the previous chapter. And then consider preemption while in the kernel mode. So again, it would be more common to have non-preemptive kernels than to have a non-preemptive. Again, it's also not necessarily the norm. And then other things is interrupts, what happens with interrupts in terms of its interaction with CPU scheduling and the transitions between the different states. So a key component is the dispatcher. The dispatcher module gives control of the CPU to the process selected by the short-term scheduler. This involves switching context. So here we have our context switch, which, if you remember, was the critical data gets swapped in for the new process. But before that, the old process's data is stored away so that when it gets access to the CPU, its current state is saved. And then we also have the situation of switching to user mode, that you are in user mode. And once the context switch has completed, with that, you can see that the dispatch work is done in kernel mode for the most part. And then we jump to the proper location for the currently running process. As it comes in, it is jumped to the proper location in its program to restart the program after its state has been restored. And then key number involved with this is the dispatch latency. How much time does it take to dispatch from one thread to another? That is an important measurement, and when you buy a real-time operating system, that is one of the measurements that they will use heavily in their advertising, is what is the context switch time. So different criteria that you may look at for CPU. Oh, so I have a new message, I think it says. Let's see how old it is. Oh, okay. It's actually an old message now. So scheduling criteria, CPU utilization. You try to keep the CPU as busy as possible, obviously. You don't want CPU cycles to go wasted. You want the ultimate throughput. You want as many processes to be able to complete their execution in a given time period, right? So you want all the process, or as many processes as possible, to finish within a given period of time. The other thing is turnaround time. How much time does it take to execute a particular process? What types of delays, either average or worst case time, does it take for an average process to be able to complete its task per unit of work? And then how much time is spent waiting by a process? Are you spending most of your time waiting? That's a problem. Or for the most part, you're getting enough CPU time so that the majority of the time is spent progressing rather than waiting. And the response time, how responsive is your system? And so that is pretty obvious, I think, is that you have a request submitted. How long does it take for a response to happen? Just from a strictly user point of view, you can easily see this as you're working with your system and you type a particular command or click on a certain button or go to a particular web page. How long does it take? That does matter. How quickly do I get some type of response? So we're going to look at one of the first way of doing it, which is the obvious one, is first come, first serve, right? You just have a queue and the processes come in order, and each of the processes are given access to the CPU in the order they arrived. So we have here a process that has waiting times for P1 equals 0, P2 equals 24, and P3 equals 27. You can see your timeline that goes from 0 to 30 with the various process waiting times. And so we can see here that the average waiting time is 17 cycles for this particular example. So moving on to another scheme, the other scheme is, what about if we do the shortest job first? So that way we can take advantage of a task actual time that they take executing. And if you do the quickest one first, you would imagine that the wait time, the average wait time would decrease. So in this particular example, if we did, what is it? 24. So I'm not sure how long. Oh, 27.3. Yeah. So anyway, let's say you did P2 first. If you did P2 first, you could imagine that the average wait time would decrease. So that is the idea for the shortest job first. And in fact, the shortest job first is the optimal solution, giving the minimum average wait time for a given set of processes. The difficulty is, how do we know which one is the shortest process? If we want to do the shortest process first, we have to know what the shortest process is. One solution is we could ask the user, but oftentimes the user may not necessarily know, or how do we prevent a process from misrepresenting how much time they are going to take. So again, we're moving on to this concept of, let me see, of that our typical swap in and out of the CPU. For the most part, it's most commonly due to I/O, and so we have the CPU burst followed by I/O bursts, and so we look at various parameters about the nature of I/O operations, and we try to figure out techniques based on that. And so the shortest job first schedule algorithm particularly relies on an algorithm to predict the amount of CPU bursts that you will have before having an I/O operation. Again, it's based on history, and the preemptive version of this is called the shortest remaining time first, because of the fact that as you have executed a certain amount of work and then get preempted, then when you're waiting to come back, the amount of time that you have has now been decreased by the amount of time that you've already worked. So that would be the shortest remaining time first. So one of the things here, and I don't think I have it doesn't look like I have a slide for this. In general, what is done here is that we try to estimate the amount of time that the job will take based on historical. So basically, the operating system try to record a history of how each individual process functions, and it uses some type of history mechanism and statistical analysis of that history to try to determine which job should be first. So one of the ways that we handle this is by giving a priority number, which is associated with each process. The CPU is allocated to the process with the highest priority. Basically, in this particular example, the smallest integer is the highest priority, and then we worry about preemptive or non-preemptive. And then the surge job first is priority scheduling, is basically giving a higher priority based on the inverse of the predicted next CPU burst time. There is a problem with starvation where low priority process may never execute. The solution that is generally done is called aging. So keep that in mind. It's a very powerful technique. if a process sits and waits and has not gotten access to the CPU for an extended period of time, there is a monitor process that will periodically go in and bump up the age of a process that has not gotten any access to the CPU. So in this way, it solves the starvation problem by slowly bumping up a process that is being starved, so that eventually it will get a high enough priority to enter in the system. So that pretty much takes us to the end of our class period time. Do we have any questions on either class assignments, material, this particular material, or any other material that we've covered? Oh, so the question is, when is midterm 2? Midterm 2 won't be for quite some time. Midterm 2 will probably be, let's see, what week are we in now? We're in week 9 or something? Who knows what week we're in? It will probably be like a couple weeks, 2 or 3 weeks before the end of the semester. I'm thinking that's like halfway in. So that will include the process synchronization area. So I think that's going to be one of the particular important topics that we have. The other is probably this chapter, CPU and memory. Let me switch to my calendar here. So we are in week 10. So yes, it'll probably be about 3 weeks. It'll probably be week 13, 12, let's see. It'll probably be week 13 before we have our midterm. And having said that, I will consider whether the midterm and final should be merged. So at this point, it's still a TBD question, but I would count on either week 13 or somehow being combined with the final. Those are the two possibilities that I can see coming forward. Any other questions? Okay, I don't see any other questions. So you guys are free to go at any time you want. You can hang on to in the chat session for this meeting, and I will answer any questions that you have. It's sort of like hanging around after class to talk to me, same kind of deal. So anyway, feel free to leave. You're certainly dismissed, and I will look forward to seeing you on Friday, or hearing from you at least on Friday.